My name's Ciaran Lee. I'm the CTO here at Intercom. And I'm going to talk about a tool we built that dramatically improved visibility into what our database is doing. It's really simple and uses a technique we call query fingerprinting. I'll start by discussing the database problems we were having earlier this year, the actions we were taking to address them, the database instrumentation that we used in our Rails app. Then I'll explain the motivation for building this new tool, the idea behind query fingerprinting, and how we built it. I'll demo it, and we'll show how it improves understanding of our database workload. I'll discuss how it helped us resolve the issues we were having with our database, and I'll finish by talking about the next steps for this tool. So here we can see API response times from our API from mid-January to mid-February. The yellow spikes are periods of degraded database performance. The red vertical lines are outages. This was a bad month. There were a lot of sucky experiences for our customers. These outages caused us to miss our quarterly availability goals. And fixing these problems was our infrastructure team's highest priority, and most of the team were working on it. So here are some of the things we did. We used a bunch of tools like Percona Toolkit, the MySQL Performance Schema, Percona Cloud Tools, which now supports Amazon RDS, which is where we actually run our MySQL database. It's excellent. We did slow query log analysis. We did 2 separate consulting engagements with Percona, who are kind of the like world experts in MySQL tuning. We had a lot of support conversations with Amazon. We now know that we ran out of read capacity, but at the time this was not clear. It wasn't clear to us, Percona, or Amazon. And fixing the problem started with instrumenting the Rails app. I think of the active support instrumentation API as simple pub sub, but the docs describe it in terms of hooks. Rails has a bunch of internal hooks that are called when certain events happen. For example, when a controller fires, a partial renders, or a SQL query runs. This is how you subscribe to active record SQL events. In this example, all we're doing is printing the 2 properties of the event, the payload and the duration. Typically, this code would live in an initializer. So now, hope you can read this code. When we load a record from the database, the hook fires and our code is called. We can see the payload contains the SQL query, and we can also see the duration was just over a millisecond. So we've been using this instrumentation technique for a while. We would parse the raw SQL query, determine the table name and query type, so select, insert, update, delete, send timing metrics to Graphite for each query type and each table, so we would know this graph, for example, shows the number of selects per second on one of our busier tables. In January, we were running over 2,000 queries per second at peak. Here we see the timing metrics for the same table. On the left axis, I think the mean shows around 1 millisecond, and the P99 on the right axis is around 250 milliseconds. This is what we would see during these kind of inexplicable database slowdown events that were plaguing us in January. Out of nowhere, latency would skyrocket, and query volume, this graph shows query volume, would hit the floor. We got pretty well practiced at failing over our database, which in this case we did after 4 minutes. That's the period where there are no queries running in the graph for about a minute or so. After we did that, query volume would return to normal, and this was just incredibly puzzling. So sometime last year, I had an idea that I called query fingerprinting. We had a few outages caused by poorly optimized queries, which are really difficult to avoid when shipping fast. We had one today. That just happens when you're shipping fast. These things happen. In our after action reviews of these incidents, we talked about whether it would be possible to get an alert when a new query ships. I had a rough idea for how we might do this, but we decided not to build it at the time. But then in January, when our infrastructure team were spending so much time firefighting database issues, we decided that it was worth a shot. And here's why. We wanted to know when new queries were introduced, which specific queries were slow, the relative differences in volume of queries running in each table, and also which parts of our app, which clusters were running certain queries. So the core of query fingerprinting is a method to generate a unique identifier from a raw query. It's really, really simple. We start off with a raw query, which you can see on the first line there. Then we obfuscate it. We remove any unique identifiers. In this case, we're removing the number 1. At this stage, we have a unique string for every query type, but it's quite unwieldy. It could be very long. So we just MD5 that string, and now we have a fingerprint. So we built this. This is how we now hook into active record events. We pass the event to an instance of a SQL metrics processor class. Hopefully you can read this. The class is 99 lines long, but I'm only showing the interesting bits today. When an instance of this class is created, it pulls a list of known fingerprints out of the cache. The record metrics method extracts metrics data from an event and sends them to Graphite. And then it queues a sidekick job if it looks like this is a new query that we haven't seen before. This works well at high volume. Any expensive work gets queued, and we only queue when we see a new query. The second interesting part of this class shows how we obfuscate an MD5, the SQL query, to get a fingerprint. It's kind of cheeky. We're actually pinching the obfuscator method out of the New Relic gem. So now when we send timing metrics to Graphite, we include the fingerprint in the key name. This gives us a load of interesting Graphite metrics, but it's not very easy to browse. We have just a really long list of metrics in a Graphite tree. So this is the worker which fires when we encounter new queries. It creates an instance of an active record model called SQL Fingerprint. So we're now saving this new query into our database. It felt kind of odd and maybe risky to store a list of database queries in the database. Certainly doing this in line would be a recipe for disaster, but the queuing technique works well. And it's totally worth it. Storing this in the database is incredibly useful. In the admin section of our app, we can now see every SQL query that has been run in our database. We can show selects only, or selects which use joins, or only selects that have run more than 1,000 times in the last day. Here are all selects that run over 1 million times in a day, ordered by volume. We can see that the top 2 queries were both run over 20 million times. These count metrics, and there's also mean P95 and P99 timing metrics. We get these into the database table by just periodically fetching them out of Graphite. For any individual query, we can drill down and see a bunch more information, including its obfuscated form, an example of a raw query, and an explain. This particular query runs 20 million times a day and does a file sort, which is probably not ideal. Definitely not ideal. We can also see query-specific volume and timing metrics, as well as count metrics that show which of our production clusters are running each query. So we can see that for this particular query, it runs 20,000 times a minute, has a P99 of 5 seconds, and it's only called from our API and ping clusters. This has been just incredibly useful for us. We now alert into Slack whenever a new query runs, and we can instantly see its performance characteristics. We also have a greatly improved understanding of the nature of the workload on our database. So back to January. As soon as we built this, it became obvious that a small number, 20 or so selects, dominated query volume. They tended to be for records that changed rarely. They tended to come from high traffic API endpoints. And these endpoints were latency sensitive and could experience outages if the database slowed down too much. So we decided to cache a bunch of these high volume queries, mainly because it would make the API less sensitive to performance degradation of our database. We thought the reduction in the database's workload would be less impactful, really more of a nice side effect. We used Shopify's identity cache gem for read-through caching. I can't say enough good things about it. It's really awesome and deserves a whole talk of its own. Using it is as simple as what you see here, including identity cache in a model and then calling fetch instead of find. It handles expiring the cache. It can cache individual records, active record relationships, and lists of records. So when we started applying caching to these high volume queries, we saw lots of graphs like this. In this case, the total number of selects we ran against a particular table dropped from around 2,000 queries per second to 125. It worked out well. It became clear that dropping query volume improved database health. The impact of database performance problems were reduced because the API clusters were just less sensitive to them. And the performance problems themselves became less common. So we kept doing it. Since January, we've dropped the total number of selects on our database from over 10,000 queries per second to around 3,000. And the problems we were having just stopped happening, and this is how we know, this is the only way we know that our problem was read capacity. It's pretty crazy that between us, Amazon, and Percona, that it wasn't obvious and no one could figure it out. So, next steps. This tool was really useful for us. We think others might find it useful too, and so we're going to open source it. There are very few lines of code. It's maybe like 300 or so all in, but right now it's closely tied to our production environment, for example, for generating our cluster-specific metrics. So abstracting it out to make it generalizable will take a little effort. It also requires a few components that everybody might not use, for example, Sidekick and Memcache. I feel like they're standard, but they might not be, so we'll need to think about whether it could or should work without them. Thanks for listening. I hope this was interesting and would love to answer any questions.
How many people were involved in this and applied and so on?
Probably, I'd say just me building it. It didn't take that long. There wasn't a lot of code in this at all, but the like list of tasks that we did, other things that we did to try and alleviate the problems that our database was having, just took our whole team. It took like 4 or 5 people for most of the month of January. We made tons of small improvements to our config, and some big improvements to our config. Did lots and lots of investigations, but for this specific thing, it was just one person.
This is all implemented in Ruby, so I'm wondering, will it cover any inserts, needs, any kind of database queries that are not triggered by Ruby, but maybe more SQL queries that you run with the approach to that?
Yeah, good question. So the question was, what happens to other queries that aren't running in our Rails app? And the answer is they're not counted. The Percona Cloud Toolkit shows metrics straight off of the database. So there's some information that you could glean from it, but we basically don't run any queries on this database that don't come from the Rails app. So for us, it's possible for people to go through our Bastion server and connect directly, but that's really rare. And we have read replicas and stuff for people to do those types of things against. Any more?
Yeah, just in terms of caching, it's more about the identity cache. Is there a strategy with expiring the cache that's used across the board, or can you tweak it?
So you can tweak a bunch of things. There's a default TTL, which I think is 5 days or something, and it expires whenever you update a record. And if you've it handles things like associations if you're also caching them, and if you're caching some sort of list query against a table, and one of the records that's in that list is updated, then that list itself is cleared from the cache. It's amazing. It's like magic. It's just so good. I really love it. All right. Thanks. Oh.
I saw you use Statsky and Graphite.
Yeah. Yeah, so the question was, how easy is it to set up and run StatsD in Graphite? It's not easy. I don't do it. It's caused us a bunch of pain. It's really not easy. It's a bit of a racehorse. There are some hosted products you can use, like hosted Graphite is excellent.